then we can maybe have a quick look at the task 27, which is this one here on impedance and admittance. And we have a not too complicated circuit with a voltage source, and the time function of this voltage source is given. And then we have some resistor and we have some capacitor. And the values of the resistance and the capacitance are given in a way that the resistance itself should be 23 ohm. And do you have a name for this? How would you call this? This 1 over, once again, what was this? Yeah, so this would be so this is called omega. Omega is the angular frequency, and 1 over omega c is the magnitude of the impedance or the reactance of this capacitor. And the unit is also ohm, so this and this, they should be more or less equal, let's say, from the value. So the current at the end should somehow split up the same magnitude of current we should have here and there, because they have the same kind of impedance. Okay, so now are the steps what we should calculate, and maybe I will try to put this on one piece of paper. So I will open up my Windows journal once again, take a screenshot of this task 27, paste it to the drawing program. Why does it not work? There it is. Make it a bit smaller so that I have some space to write there. And then also take the tasks, all the stuff that we should calculate. And then I will use maybe blue for subtask A. And we can think about, very quickly, how would we calculate impedance and admittance of this? Because this is then something that I would also like to put into the Python simulator program code.
Should we first represent it in
so, of course, say again?
in spiritual form?
Yeah, so maybe it would be a good idea at first to convert this into a phasor and say the phasor is once again square root times 2 times 230 volts, and then take E2J 30 degree. Okay. Okay, so then anyhow, how do we do total admittance and impedance of the circuit? So if we think about the resistor, what is the impedance of the resistor? It's just R. Okay, what is the impedance of the capacitor?
1 over omega c?
Yeah, 1 over omega c, and it's, so here we are really thinking about a complex impedance, so it's 1 over j omega c. So this here, as said, this would be just the magnitude of this impedance. Yeah, I think in the lecture you have discussed where this 1 over j omega comes from, or the 1 over j omega c comes from. Okay, so, but this is,
Sorry,
you didn't, so we should should I try to explain once again where this 1 over j omega?
Where did the j come from?
Where does the j come from? Okay, very good question. So then let's do a quick step back. I will use gray because it does not really, it's not really necessary for the solution of this task. But if we think about current and voltage here at the capacitor, how can I calculate so we have a voltage drop across this capacitor, or we have some voltage drop here in the circuit, the V from T, or V of T. So here we have the same voltage V of T as that is given by our source. If we have this voltage, how could we calculate the current? At some capacitor.
C times derivative of U.
Exactly. It's so let's say we have a current if the charge Q of T changes over time, and charge at the capacitor is the same as C times the voltage at the capacitor, because the capacitance is defined as the voltage, as the charge divided by the voltage. And so the C does not depend on time, so we can move the C here in front of this derivative. And then we have, okay, the current is C times the derivative of the voltage with respect to time. This is what you just said. Okay, so now we say our voltage is this type of voltage here. And I will rewrite this voltage in a slightly different way, and we'll say it's the same square root of 2 times 230 volts. And then remember what we did before in the task 26. We said, okay, e to j alpha is the same as cosine alpha plus j sine alpha. So instead of sinus alpha, what we have here in our function, I can also write the imaginary part of this complex exponential function. So I will write the imaginary part of e to j omega t plus 30 degree. Right? And this here looks different than this, but this is really from a mathematical point of view, it's the same. This term and this term. Because if we take the imaginary part of this complex exponential function, we get the sine function. So now I will take this and insert it into our voltage function here. So it's C times then the square root of 2 and the 230 and so on. They don't really depend on time, so I can put this in front of the derivative. So square root of 230 volts. And now we have the derivative of the imaginary part of e to j omega t plus 30 degree, and then derivation or derivative with respect to the time. Okay. Yeah, and now we need to calculate this derivative. The first idea is we can, the order does not really matter. If we calculate the derivative first and then take the imaginary part, or if we calculate the imaginary part first and then calculate the derivative, does not really matter. So I can also move this imaginary part function in front of the derivative. Then we have just the exponential function. If we calculate the derivative of this exponential function, so I will just copy the other terms. And now the imaginary part of this derivative. What is the derivative of the exponential function? At first the exponential function itself, so a to j omega t plus 30 degree, and then it's some nested function, so we need to have the inner derivative, and the inner derivative is j omega. Please don't call it w, it's an omega. It's a small Greek letter omega. very shy and lonely, and it does not want to be confused with some W. Okay, yeah, that's more or less it. And so now for the current, of course, I could also write that the current is some current magnitude, so some I hat times some sine function with some phase, and instead of the sine function I will also write it's the imaginary part of e2j omega t plus some phase for the current. Yeah, and for the voltage now I can rearrange this a little bit and say, okay, this j omega is something that we can also kind of, no, we will leave it inside this imaginary part, but yeah, so we can move all these terms here because they are just real numbers. We can move them into the imaginary part function, and this is the same that I could also do here. So let's move this into the imaginary part function, skip this here, say this is I hat, the amplitude of our current, which is just a real number as we discussed before. And on the other side we have the imaginary part of, now we can see, okay, j omega times c, j omega c times the magnitude of our voltage, which is what we had here before, right? This is the magnitude of our voltage, and then e j omega, my drawing tablet is a bit small for such models, plus the phi of the voltage, the angle of the voltage that we have. And closing the imaginary part. Maybe I will make this V a bit nicer. And yeah, that's it. And I mean, now we can see that if the imaginary part on both sides should always be the same for all omega t, then yeah, then this phasor must be the same as this phasor. So from this equation we get that the current phasor must be the same as j omega c times the voltage phasor on this side. And the c comes from the c, from our formula here, and the j omega is what we get from the time derivative. So a time derivative in time domain turns into a multiplication with j omega in the frequency domain. And this is what we always have. And so now if we say this equation here, I don't have that much space before writing into my camera window, but I is something times, or a current is something times a voltage. We would call this conductance, and in frequency domain we call it admittance. So the admittance of a capacitor is j omega c. This is something that I could write here and that would be useful for my task. So yc, the admittance of the capacitor is j omega c, and the reciprocal value of this, or if you rewrite the equation the other way around and say voltage is something times current, then the something is called the impedance, and if we just rewrite this equation it would be 1 over j omega c, and this is where the j omega c comes from. Yeah, and this is what we would call impedance of the capacitor. Okay, so we have a resistor, and the impedance of the resistor is the resistance, and we have some capacitor, and the impedance of the capacitor is 1 over j omega c. And so using this, and maybe what I can add is that the admittance of the resistor Yeah, and this one is not really complex, so I might skip the underscore. The admittance of the resistor is just 1 over R. And so now the total admittance of our circuit, we have two elements in parallel. Think about this like a conductance. If you want to have the total conductance of a parallel circuit, how do you calculate the total conductance? The sum. So in our case, it would be also just admittance of the resistor, admittance of the capacitor. And it does not really matter if this one has an underscore or not. And so the total impedance would just be, the easiest way to do this would just be to do the inverse of this. Or how would you calculate the total resistance or equivalent resistance of two resistors that are in parallel? If you have two resistors in parallel, if you want to have the total equivalent resistance. Yeah, the product divided by the sum. So we should also be able to calculate this if we say ZR multiplied with ZC divided by ZR plus ZC. Product divided by the sum. And so I will now go back to my Python window if I find this, and then try to do the calculation there. My mouse also already went to sleep. So there it is, but there I found it again. I will open up a new file and write some stuff there, because then I can just rerun it all the time if I do some mistakes. So the first thing that we will do is we will do the import numpy snp thing. Yeah, and then we need to have values. So we need to say the resistance is 23, and this the 1 over omega c for the capacitor I will call xc. It's the reactance, and this is also 23. And now we can say, okay, the impedance of the resistor is the same as the resistance. The admittance of the resistor is the same as 1 over R. The impedance of the capacitor is minus 1J multiplied with this reactance. And the admittance is just 1 over the impedance, for example. This would be some easy way to do this. And then I will run the script or run this module. Save it as task 27. Somewhere here. Oh, it would like to save in the systems folder. So I will just save it on my desktop. And then it's restarting here. And we can see that ZR is 23. And ZC is minus J23. Does this make sense to you? What should the ZC be? It should be 1 over J, and then the 1 over omega c is 23. So this makes sense. But where do we get the minus from?
1 over J?
1 over J. We can check. 1 over 1J is minus J. Okay. And now we can do these calculations there. And yeah, I could say, or maybe I just do it here live. So the total admittance is admittance of the resistor plus admittance of the capacitor. And so there we get some result. If we from this calculate the total impedance, which is 1 over the total admittance, we also get some result. It's 11 plus 11.5 ohm minus 11.5 j ohm. And then we said, okay, if we use the other equation here on top, the product of the impedances divided by the sum, we should get the very same result. So if I do it the other way around and say it's ZR multiplied with ZC divided by ZR plus ZC, product divided by the sum, and once again take a look at the result, we get the same one. Yeah? So this fits. Okay, we have complex impedance, complex admittance of the load calculated, Y and Z. Which questions do you have so far? So then we can try to calculate currents. So how do we get current through the resistor? And of course we will calculate this current as a complex phasor. How do we get current through the capacitor, and how do we get total current? Yeah, current divider is not super helpful at the moment because we don't have the total current, but we know the voltage. We know the voltage and we know the resistance. So we use Ohm's law and say, okay, current at the resistor is voltage divided by the resistance or divided by the impedance of the resistor, call it whatever you want. Yeah? So the equation for the capacitor we had already written there. So it's YC times the voltage, and here I could also say it's the admittance of the resistor times our voltage phasor, and then the total current, it's just the sum of the two, because this would be the nodal equation. So IR plus IC. Then I will go back to my Python script here and say the current through the resistor, and I need to have voltage, of course, at first. So I will once again say, okay, the voltage as a phasor is NP square root of 2 multiplied with 230 multiplied with our NP exponential function. And then we need to have 1j times 30 degree, and to remember that we would need to convert the 30 degree into radians, so we divide by 180, multiply with NPP. Now I'm getting more, I think, more confident. And so there is our voltage phasor as some real part and imaginary part. And think about something that is square root of 2 times 230 volts long and points in 30 degree direction. This could approximately fit, right? Okay, so now we can calculate the current IR as a phasor and say it's the voltage phasor multiplied with the admittance of the resistance, and we get something. And we can do the same for the capacitor and say, okay, IC phasor, we get this with multiplying with the admittance of the capacitor, and we get some other value. And yeah, from this, I think at the moment you cannot see that much. Yeah, so it's really an imaginary part. It's meaningful if we do the sum of the two. So the total current as a phasor, we just get as the sum IR phasor plus IC phasor. Oops, there it is. And so now if you check if we have 12 minus 7, we should get approximately 5. And we have 7 plus 12. Does this make sense?
You just doubled IR phasor.
Ah, that's why it does not make sense, right? Very good point. So that's why it's always good to do some triple check. So 12 minus 7 makes 5. 7 plus 12 makes something like 19. Perfectly makes sense. So now we would like to have these currents here as time functions back again. So how do we get time functions from this? For time function, what do I need at the end? I need to have magnitude and I need to have phase. So from our total phasor and from the individual phasors, I can calculate the magnitude. Has no attribute apps. Then the other way around. So NP apps of the I phasor. So there I get the magnitude. I can also do this for the other phasor. What should I get? What did we discuss before? The impedance here and the impedance here from the magnitude, it's the same. So there should be also the same current magnitude, and this fits. And the total current is then the sum of the two and is larger. And so here we can say, okay, the current through the resistor as a time function once again would be 14.14 ampere times sinus omega t. And we need to have the angle. The current through our capacitor as a function of time is also 14.14 ampere times sinus omega t, and we also need to calculate the phase there. And then the total current, maybe I can have this here, should be 20 ampere times sinus omega t, and we also need to calculate the phase there. Yeah, and how do I get phase? This was this command that was called angle, and this will calculate all stuff in radians, so I need to multiply with 180, divide by p, and then the p is once again not defined, npp. So there we get 30 degree for the first current, then we get 120 degree for the second current, and we get 75 degree, I would guess so, for the last current. And then, yeah, this is the result that we get. And we can think about if this somehow makes sense, and if we, what else could we do? So this is 30, this was 120, and this was 75 degree. Okay. So this is more or less the result that we should get at the end. Now in task C, or no, in the task B, we should just calculate also the total current using the voltage, not really by adding the currents. This is what I've already done. How could we also calculate the total current in task B? Do I have some space here? What would be another way to calculate the total current from the voltage?
Total admittance.
Total admittance, exactly. The total admittance multiplied with the voltage. This should also work. So let's try it out. the total current as a phasor looked like this. If this is what we calculated by this equation. If I say I want to have the total admittance multiplied with the voltage phasor, I get the very same result. So yeah, this fits. This would be another way to do the calculation. Okay, so C is what we have more or less done here. So this also worked. And then we can think about the very last task, and I will maybe use gray for this. If we have the total current and we have the total current calculated right now, how could we get the individual currents using the current divider rule? And maybe I will write this here. If I want to have the current IR from the total current, or if I want to have the current IC from the total current, how would my voltage divider rules, current divider rules need to look like?
For R would be the impedance of the capacitance over.
Exactly. So here we would say it's the impedance in the other branch divided by the total impedance, but not the total impedance of this parallel circuit, but the total impedance of this mesh. So it would be ZC plus ZR. And I mean, here it would be the opposite. It would be ZR divided by ZZ plus. This is now very small, ZZ plus ZR. Yeah, this way. I'm not super satisfied with this one here, so I will write this a bit more on top. IC equals the total current multiplied with the resistance in the other branch divided by the total resistance of this mesh. And this is what we can also check out quickly in the Python, just if this works. So the IR phasor current looked like this. Right now, if I take the total current phasor, multiply it with ZZ divided by the sum of ZR plus ZZ, we get the very same value, which nicely works. And if we take IC as the phasor, we had this value before. Now if I copy my voltage in the current divider equation, change ZZ into ZR, then we also get the very same quantities and values there. Yeah, and this is now the nice thing and the magic of doing these calculations. So everything that you have learned before, mesh equation, nodal equation, let's say Ohm's law, voltage divider rule, current divider rule, superposition theorem, nodal voltage analysis, mesh current analysis, everything will work as before. You just have to deal with complex numbers. And dealing with complex numbers with the usual calculator is a royal pain in the ass. Yeah, but if you have a computer tool, looking at my user experience today, I would not suggest to use Python, or at least not in the very basic form. Maybe if you have a Jupyter notebook, if you have a nice development environment around this, I won't say anything bad about Python. Yeah, maybe it's me, it's my fault. I'm just missing some experience there. I think I'm more used to the Octave MATLAB thing. Yeah, but this nicely works. Okay, questions so far? There's one.
For the exam, I mean, you just said that it's easy to calculate for them if you can use computer tools.
Yes.
And I know that the exam is open book, if I remember correctly.
Yeah. And the exam is in our e-assessment, e-exam center, and you have a computer, and on a computer there's MATLAB installed and there's LT-Spice installed.
Okay, so it would be smart to learn how to use those tools.
Exactly.
Like we're doing basics of Python right now, but I don't feel comfortable using this tool.
Yeah, I would, as said, I would also rather suggest to use Octave or MATLAB because they are more, it's more focused on these type of calculations, and Python is a very, very general tool. And then you always have to use this NumPy. Maybe it would be easier if, for my calculations here, I would just say instead of import NumPy SNP, if I would say from NumPy import all, and then I would have all the commands more or less like in Octave. Yeah? But the usual way to import it is like this. If you would ask Chatty, it would also suggest to do the same. Yeah. Okay. Yeah. So just to give you a brief idea, yeah, so we have done the calculation by hand. What you could do now, of course, is also build this circuit in LT-Spice and do the calculation there. And then if you do it correctly, and it would probably take me 10 more minutes to do so, then you would get the same, you should get the very same result there. Maybe we will do this the next time.